We've learned a lot about the dot product, and in fact there are two different ways that we can compute it. One is by taking the sum of the products of the components of two vectors. Let's say we have the vectors x and y that exist in Rn. We know that one way to compute the dot product if we were just given two vectors is to take the sum of the products x1 times y1 plus x2 times y2 all the way down to xn times yn. We're also told that another way to compute the dot product would be to take the length or magnitude of x times the length or magnitude of y times cosine of theta, where theta is the angle between these two vectors, and we have the following. Now the question I get from a lot of students is, how in the world is this, the sums of the products of the components, equal to this? And that is the topic of this video. So the proof is actually pretty short, and it's what I call a toolbox proof. You build a bunch of tools, you make a bunch of observations in advance, and then the proof is actually a pretty straightforward series of these observations. You say, oh, look at here, we discussed that before, this equals that. Oh, look, that equals this. Oh, we can do this, and then we're done. So that's the general format of this type of proof. So I'm going to do a bunch of observations, and then we're going to see what their implications are. I'm going to start with this version of the dot product and end up at this version. And of course, if you reverse the steps, you can go from this version to this version. Let's begin. The first observation is that I can express any vector as a sum of the standard basis vectors. So instead of expressing x like this, I can actually express it as the sum of multiples of e1, e2, e3, all the way up through en, like so. Note that the coefficients on various standard basis vectors are simply the components within the vector. Now, my next observation is that this version of the dot product is distributive over addition. So what does that mean? That means that if I had three vectors, say x, y, and z, and I wanted to calculate the dot product of x dotted with the vector who is the sum of y and z, that would actually be equal to the dot product of x and y plus the dot product of x and z. Now, how do I know that? Let's take a close look at this. I've drawn a bunch of different diagrams here, but bear with me for a moment. In this first diagram right here, we're going to take a look at exactly what x dotted with y is. Well, according to here, this formula of the dot product, x dotted with y is equal to the length of x, which would be the length of this red vector, times the length of the blue vector, times cosine theta, where theta is this angle. Now what's interesting is if we drop an altitude, so to speak, from the end of y, we create a right triangle here. And so when we take the length of y and multiply it by cosine theta, what we end up with is the length of this side of the triangle. That yellow vector is what we call the vector projection of y onto x, and its length, which is the length of y times cosine theta, is called the scalar component of the vector projection of y onto x, or the length of that yellow vector. Let's take a look at the second diagram. If we took the dot product of z and x, we would want to take the length of x times the length of z times cosine theta, where theta would be this. And what would that be? What would the length of z times cosine theta give us? It would give us the length of this yellow vector. So the dot product of x dotted with z, according to this definition, would be the length of this yellow vector times the length of x. The dot product of x and y would be the length of this yellow vector times the length of x. Now let's take a look at what the dot product between x and y plus z would be. Now I've put y here and z here, and so this dark blue vector is now the sum of y plus z. And of course, lo and behold, just as you would expect, you'd want the length of y plus z times the length of x, the red vector again, times cosine theta, where theta is the angle between x and the vector y plus z. And the length of y plus z times cosine theta would be the length of this yellow vector. That is the base of that right triangle. So the dot product of x dotted with y plus z, which is the left-hand side of this, is the length of this yellow vector times the length of the pink vector x. Now what's interesting to note here, though, is that the length of this vector is actually the sum of the length of this vector, right? Because that gets us up to about here, and the length of this vector, which is the rest of this space. And so if we take the length of this and multiply it by the length of x, plus the length of this and multiply it by the length of x, that's the same thing as taking the sum of the two yellow vectors' lengths, adding them together, which gives us this total length, and multiplying it by the length of x. So this is distributive over addition. This fact is true here. Two way less complicated other observations. One is that if you take the scalar multiple of one of the vectors in a dot product, you'll be multiplying that dot product by the same scalar multiple. This is pretty straightforward just by applying this definition. If you multiply one of the vectors by a scalar, it's going to multiply its length by that same scalar. If that scalar happens to be negative, note that cosine will also change sign, and so it will both of those negative factors will cancel out. And our last observation is that if we take x and dot it with a standard basis vector, we know that this is equivalent to the length of x times the length of the standard basis vector times cosine theta. And of course the length of the standard basis vector is 1, so all we're left with is the length of x times cosine theta, which, as you guys so expertly already know, is the length of this yellow part of the triangle when you drop the altitude from x onto the standard basis vector. Well, this happens to be the ith component of the vector x. And yes, I really do mean the part of the x vector that corresponds to this basis vector, right? So if this was the first basis vector, which I have kind of drawn it so it would be that way, this would be x sub 1, or the first component in x. So it's important to note that when you take any vector and dot it with a standard basis vector, the ith standard basis vector, it's going to extract the ith component from the vector. All right, now let's take a look here. Let's put this all together, and we're going to go from this expression of the dot product to this expression of the dot product. Well, here we go. The first thing we're going to do is express y as a sum of standard basis vectors. Just like we did above, you can take any vector and express it as a sum of multiples of standard basis vectors. I, the index of summation, goes from 1 to n. All right, next step, we're going to use the fact that the dot product is distributive. Remember this line right here. And we're actually going to take x, which is dotted with a sum of many different terms, and distribute it across. So just like we did here, and we said that x dotted with y plus z is equal to x dot y plus x dot z, we can say that x dotted with this enormous sum is actually equal to the following. All right, our next step is taking advantage of this fact, which is that if we take the dot product of a scalar multiple of a vector, that's the same as taking that scalar multiple of the dot product of the two vectors. And last but not least, we take advantage of our last fact, that if we take x and dot it with a standard basis vector, it's going to extract the ith component of that vector. And lo and behold, there we have it. We started out with just assuming this definition of the dot product. We reasoned through distribution. We reasoned through how to handle scalar multiples, what to do when you take the dot product of x or any vector with a standard basis vector, and we made it from one definition of the dot product to the other, where we have the sum of the products of the components of each vector. And that's how you can find that these two definitions of the dot product are in fact equivalent.